Building must install 25 water heaters. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot heater is guaranteed for 5 years only. But from her past experience, she knows that the probability it will last 10 years. Yeah.
Do you mean to have the Desmos up right now?
I do not mean to have it. Thank you. It looked great on my screen. Yeah. Yeah, she knows the probability it will last 10 years is 0.25. All right, so installing 25 water heaters. She's got some past experience, which gets us to the probability, the known probability, which kind of creates a connection between the concept of something that's real world application and also independent events. It's just that it's a known fact from past experience. We're just going to take it on faith. We're going to believe that this is the truth, but we're going to assume that the probability of success is 0.25. All right. So if we look at the binomial scenario, all right, we have fixed number of trials, fixed probability, independent events, and two outcomes. All right. We would evaluate this to see if it is in fact binomial. All right. So fixed number of trials, $25 water heaters. So that's check. Fixed probability. Probability of success is 0.25. Those are verifiable. All right. We have to assume independent events. All right. So independent events. But if we're assuming that the 0.25 is true, then there's no reason not to assume that they're independent events. All right. So just because one water heater lasts longer than 10 years doesn't mean other water heaters can't. Yeah, we don't, not necessarily the case that one is dependent on the other, but it could also be the case that they are dependent. You know, you think about production lines and things like that requires some real prior knowledge, manufacturing and things of that nature. If they're produced in batches, if something's wrong or defective with one item that's produced, there's a chance that there's probably something wrong with multiple items, and there is a dependent relationship mask up. So try to be subtle. Doesn't work. What? Whoops. So independent events is something that we'd have to assume, but we can't guarantee that that's going to be true. All right. Two outcomes, that's something that's a little bit more, hard and fast in terms of, the relationship. All right. It's either going to last 10 years or it's not. All right. So the two outcomes. Now, we don't have to get into exactly how many years it will last. It's just a question of 10 years, probability it will last 10 years or not last 10 years. All right. So the two outcomes. All right, so these are also values or conditions that we can check off, but they're more kind of loosey-goosey in terms of the fact that we have to make an assumption in order to kind of make it fit. All right. Also, you get the common verbiage, the way people speak, but then also you got to kind of read into what's being asked. The probability that it will last for 10 years, like on the button? Like exactly 10 years, then crap out? That's okay? What if it lasts 11 years? What if it lasts 20 years? I mean, those would be considered good outcomes. All right, so the two outcomes here would be not lasting as long as 10 years or lasting 10 or more years. All right, so less than 10 years, greater than or equal to 10 years. All right, but that's implied based off of the, just kind of your understanding of the way things work. If I say I want to get 10 years out of this car, I bought a car, I want to get 10 years out of it. You're not hoping it dies the day after the 10th year has elapsed. Like, oh, the 10-year anniversary of me purchasing this car. The next day, it's okay if it craps out. No, I'd still like it to run. I'd like to get some resale out of this. So you got to think about, all right, well, what are they saying, but what do they really mean? All right. Now, in the question here, it's saying use a normal curve to determine the probability that 8 or more of the 25 water heaters will last at least 10 years. All right. So we get a little bit more explicit with what the question is asking because you kind of have to. All right. But the normal curve, well, they're saying to use a normal distribution. All right. So that means z-scores. If we're going to use a z-score, then we're going to have to find the mean and the standard deviation. All right, so the mean, if we're assuming this is binomial, the mean would be computed by n times p, and the sigma would be the square root of n times p times 1 minus p. All right, so number of trials, 25. Probability of success, 0.25. So it's going to be 6.25.
Is the standard deviation the square root of n times the probability, or is it n times p 1 minus p?
N times p times 1 minus p under the square root. All right, with the p being the probability. I'll actually kind of do it like this. So I can zoom in. All right, so n times p, 0.25, I'm sorry, 25 times 0.25. 1 minus 0.25 would be 0.75 under the radical. So we'd have to crunch that. So the square root of 25 times 0.25 times 0.75. So about 2.165. All right, so that's my mean and standard deviation. All right, but it's population because we're dealing with, even though we haven't listed out an entire probability distribution, there is a probability distribution associated with this that we could list out. There's 25 water heaters. Maybe none of them last at least 10 years. Maybe only one of them, maybe 2 of them, maybe 3 of them, maybe all 25 of them, and everything in between. All right. So if I want to find the probability that 8 or more of the 25 are going to last 10 years, I'm really looking for probability that the random variable x is going to be greater than or equal to 8. All right. I have to convert that random variable x into a z-score. So z, is individual score minus the mean divided by the standard deviation. So this would be, in this context, x minus mu over sigma. I'm going to shrink this down a little bit. Over. So z is going to be equal to 8 minus 6.25 over 2.165. Which we can compute here. All right, so we're looking at a z-score of about 0.808. it is a normal distribution question, so I need a graph to go along with this. You know, the normal curve with the labels and all that jazz. You know, it's not ideal, but we got to do it. All right, so you could tuck that really in anywhere. I'll just kind of just put it off on the side here. Yeah, Luke.
Can you kind of like explain your thought process with like how you're doing this? Because I feel like I'm just kind of copying down notes and not really understanding.
So if we're going to use a normal curve, this goes back to the beginning of the unit. If we're going to use a normal curve, then we have to use something like normal CDF in the calculator to come up with the area bounded underneath the normal distribution. So in order to do that, we need to know the mean and standard deviation and compute a z-score. All right, so what I'm looking for is when they say 8 or more, I'm looking for the z-score corresponding with the x value of 8 so that I could find the area to the right of that under the curve.
So that normal curve is just like the same as the normal CDF.
Exactly.
Okay.
Yeah,
So
so
whenever we see like normal curve on like any question in this class, just like assume.
exactly. Normal curve means normal CDF means z-scores.
I
Yeah.
was confused for a second.
Yeah. Yeah, we're bringing back something we haven't looked at in a while,
Yeah,
so
okay.
it'll happen. It'll happen. So the mean 6.25 was the middle value. You know, it's the middle of the hump, and our standard deviation is 2.165. So if we go out 3 steps to the right and 3 steps to the left, this goes back to that recurring theme of just trying to get the full credit for something that it just feels so unnecessary, but it is what it is. It's the AP requirements. So 6.25 minus 2.165. So 4.085. Minus another 2.165. But I could do it like this, you know, bring up the previous computation and just kind of tuck in, you know, second delete, tuck in at 2 times. And you get a 1.92. Tuck in a 3 and make it recompute, and you'll get a negative 0.245. And then we just got to do the same stuff, just going the other way. All right, it's kind of brutal. All right, I'm just going to get the outermost one first. 12.745. Bring it in closer. Only 2 steps. 10.58. Bring it in closer. Only 1 standard deviation. 8.415.
Wait, why?
I'm just counting out in terms of standard deviations.
Oh, you did it backwards.
Yeah, I just did it backwards though, yeah. Because I already had the most recent calculation was minus 3 times. So it was easier for me to just change that to a plus. All right, so what they're looking for is the area to the right of 8. So we would eyeball that. It's going to be somewhere in this neighborhood here. We're looking for this area. All right. Now, the question that they're asking is the probability that x is greater than or equal to 8. We interpret that as the probability that z is greater than or equal to 0.808. And that's where our normal CDF stuff comes into play. Just bearing in mind, they don't want to see the normal CDF. And in fact, I mean, I've been led to believe this. I don't know how true it is. That writing calculator speak as a solution on the AP will actually work against you. Right? They don't want to see it. Just don't even do it. Don't write normal CDF, normal anything. Just the notation P of Z greater than or equal to 0.808. For whatever reason, that seems to be more valuable to them. Right? But what we would do is we go second vars, option 2. The lower bound would be 0.808. The upper bound is something big. All right, something big like 10, 1,000, 1E99, with a mean and standard deviation of 0 and 1, and you get 0.2095. All right, so approximately 0.210. All right. So that would be the normal distribution approach to solving this. The problem is, and it's pretty substantial in terms of the issue that arises from doing it this way, but there is a way to correct for it. The issue is that this is a continuous distribution. All right, the normal distribution is a continuous function. So we don't just get, I mean, you could even tell based off of the values that make up the scale. You get a lot of decimal values. But we're not looking at continuous data. We're looking at discrete data. The only values that make sense would be whole numbers for water heaters. Like I wouldn't be looking at 6.25 water heaters. Right? If I only had 0.25 of a water heater lasting for at least 10 years, that's basically saying that there's a water heater that isn't lasting for at least 10 years. Right? Because if only a quarter of it is working, then it's not working. All right. So, I mean, I suppose it would matter like which quarter of it is working. You know, like if you have a car and 25% of it is functional, you know, it's like, okay, cool, how much is my car worth? I mean, it's not going to drive if only 25% of it's working. Something critical is missing. But if I wanted to, you know, sell parts and make some money, if the 25% of it is the engine, that might be valuable. But if the 25% of it is, you know, the upholstery, then, you know, you might get some money if it's clean enough, but it's not going to be what you would get if it were the engine. All right. So we need to correct for that. All right. The decimal values don't make sense in this context. All right. So let's see what the probability would be if we used just binomial probability. How does this result compare with the result we would obtain by using the formula for the binomial probability distribution with n equals 25 and p equals 0.25? So what that would be is the probability, again, that x is greater than or equal to 8, which would end up being, if you were to itemize this and break it all down, the probability of getting 8, or x equal to 8, plus the probability that x would be equal to 9, plus the probability that x would be equal to 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. All right, so we would have to figure out all of these probabilities and add them together. All right, so that's one approach. And I'll show you that approach in a second using the list function. Or we could use binomial CDF. All right. So into our calculator we go. So into the stat editor. we would have we would need the values of 8 to 25 populated into L1. All right. So you type in 8, 9, 10, 11, 12, and so on, or you could use a sequence function. So second stat ops 5 XX 8 25 going by ones. All right. So that would be the sequence that I would put in. Now, you could also put it, I mean, if you have the older model, it would come up when you do second stat ops 5. It comes up like this. It'll say sequence. You would type in XX, right, and then whatever your start is and whatever your stop is. Right, in this case, 825. All right. The reason why it's written this way is because this is your expression and this is the variable. So this corresponds to, I mean, I know this is like kind of variable in terms of whether or not you would have seen this before, but if you have any experiences or any experience with sequences from Algebra 2, technically it's supposed to be taught in Algebra 1, but I can say personally, I never got there. You know, like we always run out of time. So if you have in Algebra 2, maybe in pre-calc, definitely if you're in BC, you saw it, but A sub n equals n would be a relation indicating a sequence of values where n is greater than or equal to some value a. All right. Well, I already used a, so I'll say whatever. But in this case, it would be 8. All right. So what this is saying is that if I start off at 0, I'm sorry, if I start off at 8, the 8th value in the sequence would be 8. The 9th value in the sequence would be 9. The 10th value would be 10, and so on until you get to whatever the maximum is. And I'm saying the maximum is 25. So I can make it a compound inequality, but that's kind of a little bit more than we need to get into here. But what this is saying is, at least for this part, that's giving the rule of the sequence. All right. So we use x instead of n. This is giving the variable that's used in the rule. So if I use an n here, I'd write n here saying that that's what the variable is. All right, because otherwise it'll treat the variable or whatever you type in as a letter, it'll treat it as a string constant. All right, so you put it as a string, the calculator interprets that string as a constant. All right, so based off whatever's already stored in there. All
So
right.
they always have to be the same.
So they always have to be the same. Whatever variable is in your expression has to be indicated as your variable. All right. So you paste that. All right, but actually, without even realizing it, I put it in the wrong cell. You got to put it in the column heading, otherwise you're going to get an error. I'll show you the error. It'll say data type because you're trying to put a sequence of values into one cell, which doesn't make any sense. So I would quit. Nobody likes a quitter. Go right up into the column heading, enter, so that you apply the rule to the entire column, second stat ops 5, then your XX825. All right. Then I would go on to L2, hit enter, so that I can apply a rule to this entire column, and that rule would be binomial PDF. All right. This will allow me to get probabilities associated with each one of these x values, because sometimes you need the distribution as well as the total. All right, especially if you have a bunch of questions that are related to the same information. You know, this one says x is greater than or equal to 8. It could very well be followed up by a question that says x is greater than or equal to 10 or 12 or whatever, you know, and so you can modify your table after that. All right, but second vars binom PDF, all right, so second vars binom PDF, number of trials is 25, probability of success 0.25, your x values are stored in L1, so you'd hit second one. All right, and it brings up a paste The paste function, again, is just, well, literally pasting that command as a line into the command field. But if you have a older calculator, that's what you type in anyway. All right, when you hit enter, it populates the entire list with all of the associated probabilities. All right, so if you needed to, you could actually write these values down if it were required. On the AP, they're not gonna give you 25 as your value of n. They'll give you like 15, maybe 12, and they'll say x is greater than or equal to 8, and then they'll expect you to write each one of those individual probabilities down, and then also the sum. All right, so this is a nice way to get all the probabilities in one shot. So if you needed to write them down individually or refer to them individually, you could. All right. So then after this, what I would do is take the sum of all these values, right, using the sum function. So I'd quit out of here, second mode, and second stat, math 5, brings up the sum. Second stat, math 5, brings up the sum. Tell it to add up all the values in L2. So sum of L2, again, that's second stat math 5. All right, second stat math 5, all the values in L2, that's where all the probabilities are. And at long last, I get 0.273. All right, now this number should not match what we got in number 1. All right, because we just used a discrete approach. The binomial probability theorem involves only discrete values, so the 8 only, the 9 only, the 10 only, not the little decimal values between 8 and 9, 9 and 10, 10 and 11, and so on. All right, so we would need to reconcile the answer that we got here with the answer we got for number 1 in order to use the technique for number 1 instead of the technique that we used just now. All right, so for very large sample sizes, especially if you had something like, 25 water heaters, you have 250 water heaters. You'd probably want to use a normal distribution for something like that rather than itemize it. Pierce, question?
Oh, I was just thinking, so like you were saying, basically with more trials, like that difference is just going to increase between the two.
So if you wanted to, you could use binom CDF. So second vars, option B, trials, 25, probability of success, 0.25. Remember this X, it just says X value, but this is really the maximum X value. All right, because binom CDF only works as an at most. We need an at least. So in a discrete random variable, we look at least n, whatever it happens to be, at least your number, is equivalent to at most 1 less than whatever that number is, but that result subtracted from 1. All right. So really, I just want I want everything else except for the 8 to 25 to be plugged in here. So I'd go up to 7. And then get that answer, this answer, and subtract it from 1. All right, and you'll see you get the same thing. So if you just need the answer, you might say something like 1 minus the binomial CDF. So we wouldn't write that. We would say the probability that X is less than or equal to 7, and that would give us the same value, 0.273. It's decimal points off at the end, but close enough. So how do the answers compare? There's some variation due to the difference between continuity and discrete variables. So variation due to the fact that continuous method was used in a discrete situation. All right. And again, the discrete is just a whole number of values. You can determine a value of a number or an item or an object, or determine an individual's value just by looking at it. You know, you're not going to be able to do that for height, weight, time, temperature, and things like that. But I can count water heaters. All right. So if I needed to count the temperature of the water within the water heaters, that wouldn't make sense. I'd need a thermostat or thermometer for that. All right. So then, number 4, how can we modify number 1 to give a more accurate estimate of the probability? Well, I have a 0.210 as the probability. I really should have something a little bit bigger. All right, it should be 0.273 instead of 0.210. So I'm off by 0.06-ish. I need more space. I need more room to roam. All right. So what I'd have to do is take this and smidge it to the left a little bit. All right. So if I could do that, that would give me some extra area, and that might be enough. All right. So I'm over here at 8. What if I dialed it back really to any number that would round to an 8? You know, like 7.5 would round to an 8. Right? So account for some of that little extra x value that would get me even still to an 8 numerically. 7.5 rounds to an 8. Everything between 7.5 and 8 would round to an 8. If I include those values, maybe that's enough to get me close enough to the true area that I could use this as an approximate. So if I just kind of smidge this over to the left a little bit, over to 7.5, maybe that would get the job done. All right. So what I would have to do is pretty much everything all over again. It's really not that bad. I mean, we're really going to do everything all over again, but not from scratch. You know, so I'm going to be looking at, all right, well, what about the probability of x being greater than or equal to 7.5? A little bit thicker on the marker here. Going to make it blue. So that's going to impact my x value, which in turn would impact my z-score, but the computation should be pretty easy. All right, so everything else is going to remain the same, but it's all going to be calculator work. So, you know, if you could find it, the previous computation, wherever it is, it's like an hour ago, so I'd have to go get it. But I would change that 8 to a 7.5. At this point, I could have just typed it in from scratch, but, you know. But this is what I would be looking for. Brand new z-score, but same structure, just different x value. Yeah.
Why'd you write 7.58?
Oh, no. So, crappy handwriting strikes again. This is an 8, and then this new point is a 7.5.
How would we like represent both of those? Like we'd have to represent both of those?
Yeah,
So that's the like modified.
yeah, exactly. Maybe just draw a little arrow.
Can you explain again though why like we're modifying it to 7.5 to make it more accurate?
Because we know that the correct answer, the correct probability, was supposed to be 0.273. But when we did it with the normal probability, or normal distribution, we came up with 0.210. So in order to get more area, more probability means more area, I'd have to move my X value to the left. It's just a question of how far to the left. So what we did was we moved it to the left to 7.5 because it's kind of like a justification. It's sort of like a little wishy-washy, but it's basically saying, well, 7.5 is really 8 anyway if you round it. Yeah.
So, like, it would be fine to say any number as long as it's like above or at least 7.5 and between like 8.
Right, exactly. So, I mean, if we said, okay, well, let's try 7.9, 7.7, whatever.
It'll still be more accurate.
Exactly.
It won't be like too far away.
It'll be better than the 8. It may not be as good as it could be. There's going to be some perfect value that'll get it to land exactly on that number, but close is good enough for this.
Yeah.
All right.
So that's just the explanation.
Yeah.
Thank you.
Yeah, no problem. So that's going to be about 0.577 as the z-score. So I need the probability that z is going to be bigger than that, bigger than or equal to that. And hopefully that's going to be something closer to 0.273 than it was before. We're going to find out. So second vars, normal CDF. On the low bound, we know it's 0.577. On the upper bound, something big. Paste it in. Yeah, we got 0.282. So we went too far. But it's an approximate value, and 0.282 is a whole lot better than 0.210 was. All right. We went from being about 0.063 off, well, exactly 0.063, to being less than 0.01. 0.01. All right, so we're definitely at a higher degree of accuracy. All right, so what we're going to learn going forward is how to get to an even better degree of accuracy. All right, and that's kind of where inferential statistics comes into play.